So in the previous video, we discussed a generalized case of how to define an efficiency that we called eta of our system, where we had some useful power that we're trying to transmit in the sideband, right? So we have this useful sideband power, and then we have the carrier power, which if you add too much of it is just wasted, right? We want to add a minimum amount of this. So that's this carrier power. Now, this is the efficiency for some general message, right? We don't know what this message is. It's just some message signal that contains new information. Now, let's go back to our friend that we call a special case that we call tone modulation. Okay, in our special case, our message consists of a single wave at a single frequency, right? This omega m. So this is our message wave, and our message their special tone message has some amplitude B. So let's figure out what the efficiency is for this special case, which we call the tone modulation. So we can define our modulation index, right, as the ratio of B to A. So this is the amplitude, right, of this message signal to the amplitude of that carrier. And we can define that modulation index in terms of this B, the amplitude of our tone modulation. And we can then rewrite our message using this ratio between mu, the modulation index, B, the amplitude, and A, the amplitude of the carrier. By doing this, we can therefore write that for this special case, for our special case where our message is one tone, we have a time averaged mean, which is this squared divided by 2. So we have a very special case here where we can substitute this message time average power for this amplitude squared over 2. Okay, and this means that the efficiency can be rewritten by substituting this mu a term in for all of the places where we saw this message square term. And we can further simplify it by bringing out the a square terms and canceling those into this equation. So for the special case of tone modulation only, we have an efficiency that is governed entirely by the modulation index. Now, in this case, right, we could recall that the modulation index should be somewhere between 0 and 1. And this was what was seen in those previous videos in chapter 4.3, the introduction video. So we needed this modulation index to be between 0 and 1. And if you recall, we said that if the modulation index is exactly 1, that was basically the bare minimum. And then a larger mu, that means a smaller a. So if you make this mu larger, push it this way, that means that your amplitude A, the carrier coefficient, the carrier amplitude coefficient is smaller. All right, now if you want the best case scenario, this means that your mu is equal to 1. So you've gone all the way over here in the best case scenario, and you've just barely lifted that message up across here. So if your message was to here, right, you've just barely lifted it so that the lowest part of your message is just above 0. So that's the best case scenario. You get a mu of equal to 1. So when your mu is equal to 1, and you have the best case scenario, you've chosen the best possible A, the best possible carrier amplitude coefficient, that your efficiency is only 33%. So in the very best possible case, when you're sending just one tone, one frequency tone, the best you can do is get 33% efficiency for our AM modulation, for our amplitude modulation. So clearly that's not that great, right? So what about for practical signals? Well, for practical signals, the message power is not equal to this ideal case, right? This ideal case where this was the amplitude of our tone message. So in a practical signal, we don't even have the message power being equal to this. So that means that we can't even get this efficiency, right? We can't even get our message to be this large, quite as ideal as this. So overall, amplitude modulation is not a particularly efficient system, but if you have many different users, right, you may still be able to save some money, right? If you have hundreds of users who each can use the envelope modulation instead of coherent modulation, the transmission of the signal, right, that signal sideband power, it might not be that efficient, but you still might save some money overall by having just the sheer volume of receivers. And one last question, how do you do this AM signal generation? Well, the way that you can do AM signal generation is go back to the circuits and components that we used to make the double sideband modulation. And then at the very end, right, so make something that does the DSB SC, which we saw a number of these. And then at the very end, put this into some summer, something that can add in another output, another signal, which has your carrier. So this, by this method, you could start from your DSC double sideband single suppressed carrier, and you could get a AM modulated signal. All right, thank you, and see you in the next video.